right. So, good morning, everybody. I guess people are coming in together, so we'll start the day. With a little bit of recap of what we did yesterday. So yesterday was great to have you all here, and thanks for the engaging conversations. It was fantastic to have people who are developing advanced tools to give us a glimpse of what they're doing, from large scale recording in terms of microgrids all the way to single cell resolution voltage imaging. And that was very impressive to see all that work. And then after that, we followed by conversations around the ecosystems for data archiving and creating platforms for sharing the data. And then we followed with the next session, which was all about how to make sense of these things in a way. And today we have a very packed day for you. So it's full of cool talks, one after another. And we'll start with Mackenzie in the morning. So she'll give the keynote speaker. After that, we'll have 3 more sessions today. And in between each session, we'll have one panel discussion. So I asked the moderators to keep all the speakers in track, that we don't bite into our time. And we can have an engaging discussion like yesterday. And at the end of the day, we'll have a discussion session to recap what we have heard about and what are the future ways to solve these problems. So it's my pleasure, actually, to introduce to you Mackenzie Mathis, who was actually here in Boston. And I think maybe she didn't like the cold, so she used to be in Rowan Institute, and now is actually a professor at EPFL. And she does really cool work in terms of quantifying behavior for understanding the organization of behavior, and her work has been fantastic in terms of not only impact of what she has produced scientifically, but also from the point of view that it has been open out and available to all the other people to use it. And I think that's a great example for what we aspire to do. And I think that's a good example of open science built on cool new methods, but also effective and available to everybody. So one of the product of her lab has been Deep Lab Cut, which a lot of people use to basically quantify the behavior of the animals. And then lately, in the last year, there was also a very cool paper called Zebra. I don't know why not zebra, but Zebra. So maybe she talks about it a little bit today. But that was also an interesting paper in finding latent dynamics. And I think collectively her work has been very good in terms of how do we build this sort of algorithms that utilize the advancements in AI and the modern measurements to find meaningful behavior and relation with recordings. So without further ado, I actually give the podium to Mackenzie, because she has much more interesting to tell us. And I'll keep time on you for 20 minutes, and then we'll have a few questions, and then we move to the next session.
Okay. Thank you
Please
so much.
give her an applause.
No. Yeah, thank you very much for the very generous introduction. I'm super happy to be here, and I found yesterday very inspiring. I thought it was really fantastic to talk about, from my perspective, how the sausage was made, right? How we actually collect the data, what's the new tools that are coming, and hopefully today we're going to hear about what you can do with it. So I really wanted to jump right in with probably a very old to many, but maybe kind of new in some ways, thinking about levels of abstraction and where we actually want to collect data from and how we want to analyze it. So in general, I think many of us in the room are very much interested in sort of this hierarchy, if you will, of going from genes to behavior and including modeling animals in their own environment. And so this is kind of my adaptation of inspired work from John Krakauer, Daniel Bassett, Terry Sinofsky, and of course David Marr with the levels. And I think now we're in this really cool era of being able to leverage and build new AI that not only works in larger computer vision domains, but actually works for us in life sciences. So I just give you a few examples here of I think, kind of the levels that I'm really deeply interested in and trying to link across them. But concretely, if we sort of break this down even further, if we think about what we're ultimately trying to get at, right? What are potentially the mechanisms of this adaptive behavior and how genes might give rise to this, which might be an ill-posed problem, but we can debate that as well. I really focus on the kind of this computational and algorithmic level and leave implementation up to all of you. So in my group, we're really interested in this kind of bridging the gap and thinking about how we can not only link neural activity to behavior, but ultimately how we can link these computational algorithms to really theoretical understandings of this, right? So on the left, you see probably this familiar diagram about computational algorithm and implementation from David Marr. But for me, it really comes down to what John Krakauer nicely summarized is, why, what, and how. And so in my group, we try to work mostly in this computational and behavior space, but we're, of course, very keen to leverage and use data and work with many of you to try to make sense of this all. And we do a little bit of actual systems neuroscience in my group as well. And so since it's a short talk, I'm, of course, not going to dive into a lot of details about these topics, and I just want to highlight a few of them. So I want to jump right in by just bringing up Deep Labka. Thank you, Nima, very kindly for raising it, but this has been a large component for me because I think behavior is not by ill design kind of at the top of the pyramid for me, right? Like ultimately I'm trying to understand how muscles give rise to things like reaching and what are the circuit mechanisms all the way from cortex to spinal cord that actually enable this adaptive behavior. And so measuring it became really critical. I'll spare you all the stories of trying to track tiny mouse hands prior to deep learning. But over the last years, we've been pushing hard on this and not only trying to make advances on the AI side with things like showing how you can use little data to do transfer learning such that an end user can annotate very few frames, which might seem very ill-posed if you're training a model with 50 million parameters. And so I just list a few examples here, but I think from the open science perspective, very early on, I was really passionate about democratizing this and making it easy to use. So you can use this in the terminal and use 12 lines of code to have access to everything from project management to selecting frames to label that are maximally diverse, to training deep neural networks, to evaluating them, and then building videos with this. So I just give a few examples here of everything from cells to social marmosets, which were taken here at MIT. So lovely to be back. I'll give you just 3 quick slides on teasers if you're familiar with this already. So sorry for those of you that might not be. This might be a little too specific. But one thing we've worked on in recent years is this very challenging problem of animals that are very closely interacting, like these marmosets, of course, they can be occluded from each other, from the environment, et cetera, and you want to keep the identity of these animals really separate. And ironically, humans don't interact this closely, at least in video, that's public, so animals are a really interesting test bed for that. But that being said, there's a few benchmarks in human pose estimation. So we just presented last week work in Paris at ICCV where our new algorithms actually top the benchmark in human pose estimation. So I think this is a nice transfer of actually taking principles that we learned from animals, like non-human animals, in the laboratory and actually being able to make an impact in a much broader scale. But one of the things that has always kind of struck me with this, the transfer learning approach is, could we actually build better base models? Can we build something like foundation animals for pose estimation? So along with a really talented PhD student in my group, we've been working to do this. So I always like this slide because I hope I can have like the most species per talk. It's sort of a self goal. But nonetheless, so we've been working on methods to do this. So I wouldn't say that these are the final models, but I think what we do in this preprint is lay down kind of a recipe, if you will, of how to take data that might be very differently labeled. There can be annotator bias, there can be domain shifts in the data. Obviously, giraffes and squirrels look very different. And how can we actually amass this to build models that don't have catastrophic forgetting, that can learn from all these disparate data sources, and even be adapted on the fly in near real time to your own data? And so we're pretty excited about these types of things, and everything is already publicly available. So if you want to use these models, I think this is another component that Nima raised, I think this preprint is in its 3rd revision over the last 3 years because we just continue to make advances, but it's always been done in the public. So that way you could really see the code, use the code, test it, we get user feedback. I think that's been a really critical process for us. So I think it's kind of the best case example, if I can say, is like anti-scooping because we're coming together as a community, right? It's like a call to action to bring people together to make something better for all of us. Kind of on another realm, if you will, we've also been, probably like many of you, really intrigued by the recent advances in large language models. So we built this system, which we call Amadeus GPT. Very briefly, what this allows you to do now is to interface with code with natural language. You've probably heard from my questions yesterday, I don't think everything should be hidden behind front-end GUIs, but I think at the same time we want to allow access and make it easy for people. And so what this actually does under the hood, there's a series of maybe 4 large language models that can take in a query like, when is the mouse on the treadmill? Of course, the model doesn't know where a treadmill is, so it might ask the user, can you identify what the treadmill is? So it would run an object segmentation algorithm, find the treadmill. You could say, okay, object 5 is the treadmill. It would run pose estimation automatically, and then show you the code that it actually wrote to do this. If there's errors, it will debug itself, and then output the video. And so it has like this explainer and kind of educational component to it. So I think this is a proof of principle. I think there's way more to do. It's no near like a product that I would ship to everyone, but you can play with it. So it's there, and everything will be, of course, open source, and this is just accepted to NeurIPS. So just to give you a flavor of this, you can really ask queries, and it gives you the output and things like the code. This is a bit condensed for the talk, but nonetheless, hopefully that gives you a sense of the point. So we're really eager for feedback as well, because this is, again, very much community-focused. And so with that, I would be really remiss not to say that all of this is built on other giants of open source software. So Deep LabCut is built in Python. We heavily leverage Matplotlib, NumPy, SciPy, early versions in TensorFlow. For those of you following along, we are actually, we've rewritten the entire backend, and the new version that will be out by the end of the year is all in PyTorch. Which makes things a bit easier, and also PyTorch went to the Linux Foundation recently, so it's truly open source and not in the hands of a company. We offer things like interacting in Jupyter, Jupyter Hub, Google Colaboratory, of course the terminal, my favorite. Everything's on GitHub, so you can quickly iterate and play with the code. And we also provide large-scale pipeline computing, so we've maintained a Docker hub for many years and instructions to get you started with Docker to move this to AWS. We've been big fans in my lab of DataJoint. They don't pay me to say this, I promise. So we helped with them with an Elements for Deep LabCut, so if you want to use this in your laboratory, it's there. And then I'd say kind of the thing that I'm really most excited about in some way is that people build on this, right? This would have been a terrible waste of effort, time, and money if no one used these tools. And so, the outputs are HTF5 files. We also have a conversion for NWB. But there's a lot of references here, and I'm happy to share these slides, but these are all publicly available. At the same time, in the spirit of open data science, I want to go even further. So aside from the YouTube videos, which I guess a lot of people like to watch me program in the terminal, you could also come and do it in real life. So we established the first AI residency program for underrepresented groups in machine learning and computer science. And you essentially get to come and spend the summer with Alex and I in our laboratories. We open up everything. We do it in the public. They're fully paid, so we really want to make this accessible no matter where you are in the world. We've been thankful to the support of the Chan Zuckerberg Initiative for funding this, for NVIDIA, and EPFL sources as well. So if you are interested, the application's open on Friday for next summer. So if you also know like undergrads or PhD students that want to do a residency in our program, this year's cohort has been working on a new paper with us, and so I think it was also a really exciting, learning development, and we learned from each other. So it's been really fun. So this would be our third year of this program. Okay, but in the last 10 minutes, I want to get to kind of the meat of what I wanted to talk about today, which is what to do with all of this large data that you're collecting. And so the way that my group is thinking about it is, I'd say, largely divided into 2 categories. One I'll call data-driven modeling, and the other is task-driven modeling, which I don't have time to talk about today. So just in 10 seconds, the notion here is you could constrain artificial neural networks based on a particular behavioral task to, say, test a hypothesis of the system. So imagine if you think that proprioception is used for action selection or trajectory decoding, you could train artificial neural networks on, say, synthetic or biomechanic or real muscle data, and then scale this up and try to understand the differences between what emerges in these neural networks, the representations, but also how well they can explain the variance of your real neural data. And I think we'll hear more from Martin Schrimpf about how this has really been elegantly done and pioneered here at MIT by Jim DeCarlo's lab. We just happen to focus more on sensory motor control. But the other side is this data-driven modeling. So I think this has been touched on a bit. I think Matteo's talk listed a few things that can be, that they looked at, and maybe some differences, which we could debate about. But in short, there's things like single-cell analyses, like GLMs, all the way to things like using ANNs to actually understand what type of representations emerge from this data. And so I really like this for two reasons. I think that, of course, the single cell is really exciting, but at the same time, we know that neuropopulation dynamics can lead to understanding things like neural computations that we couldn't see at the single cell level. So this top example is from Mark Churchland's group looking at population dynamics in M1, where an animal is doing a cycling task, and the color is based on the speed, and then you can see the principal components of this population. But any one single neuron didn't actually show this differential coding across the population and changes of speed. We've also touched on this a bit yesterday, that the fact that I think in Ali Pasha's talk, it kind of kicked off this comparison of, how much neurons, how many dimensions, how do we have to actually do this, what does it mean? I think a lot of the ways that people are thinking about this, and including this top example, is also using linear methods. But I'm going to argue pretty strongly today that it's challenging to assume that anything should be linear in the data that we collected. And so with that, I kind of want to walk you through the thoughts behind the algorithm. So at the end of the day, I want to argue that many of us actually care about these hidden, aka latent, factors in the data that actually give rise to what we can observe. And so you can imagine that there's some series of Zs or latents that are potentially mixed with some mixing function here, so xg of z, that give rise to the spikes that we can actually record. And in try as best we can, we saw in the IBL data, maybe we can't even get it exactly in the right spot, but we certainly can't record from the exact neurons from every animal. So when we even put in our neural pixels arrays, or we put in our 2-photon, we haven't picked exactly those neurons because we know that they statistically represent all of the latent spaces, right? So we want to oversample, we want to collect a lot of data, and ultimately what we want to do, though, I'd argue, is that we want to understand something about the true underlying latents of the system. Can we actually back calculate what these latents are? And you could either do this in two approaches for the aficionados in the room. You can do this by writing down a series of dynamical systems equations that sort of does it in a generative way where you know theoretically what you might be looking for, or you can learn this, but this has been hard. And so that's the problem setting that we wanted to start with. And you can also think of this from another viewpoint as a dimensionality reduction. And so the problem setting that we're thinking about effectively is nonlinear ICA, nonlinear independent component analysis. All right, so what actually happens when you use one of these dimensionality reduction algorithms? I think this is another example of why you don't want to just click a button. We want to understand what we're doing with our data. But in short, you take neurons over some time window. So this is neurons by time. This is eventually a population vector. All of these neurons are a really high dimensional space, and ultimately we want to be able to cluster them together to capture these lower dimensional latents in an embedding space. And so there's a whole plethora of really amazing tools. Obviously, I'm not going to go through all of them today, or any of them, frankly, but this is effectively what we want to do. And so when we came upon this kind of problem several years ago, we kind of made a laundry list. So just very briefly, we wanted them to be interpretable, i.e. we wanted to understand at least the decodability of the state. We wanted them to be consistent, so that's the C, not the Z in zebra. We wanted to be able to find similar latent spaces if they truly exist across runs of the algorithm. So if you run it, you should get the same answer every time. Coming back to spike sorting, I was sort of freaked out by that discussion yesterday. I was like, whoa, okay. So it should really produce the same thing every time. And have something like a goodness of fit metric, right? How much variance explained, if you will, from the PC space, but this is a nonlinear space. It's a little bit different. We didn't want to have any assumptions on the data type, the data generating process, this xg of z. So we wanted to be able to use calcium spikes, EMG, whatever you want. We wanted to be flexible to use both continuous and discrete data, and use it in several modes, namely for hypothesis testing and also for data-driven or discovery-driven analysis. And I think one of the last ones is just sort of a functional nicety of all of these things. If they're constrained, we could then combine this across animals, because it's not that we get, not all of us have the Ali Pasha level of imaging data yet, and so we want to be able to combine maybe from different animals and different recordings. And so in all of the systems that we've kind of referenced in terms of behavior and systems neuroscience have something like a data set like this. You have neural data. You might collect things like behavior. It could be pose. It could be trial. It could be reward. It could be the state of optogenetics. It could be learning rates. It could be the history dependency of the animal. These are all potentially auxiliary variables that we can use to potentially guide this embedding space. But in a purely unsupervised way, minimally, we could use time in neural data because we always have it for free, essentially, and there's an assumption that something is changing over time when we're making recordings. And so just for the brevity of time, I'm not going to go through the math, but very briefly, you can use a nonlinear encoder model like a CNN or a simple MLP or an RNN, pick your whatever you like. The magic, if you will, of this algorithm is contrastive learning, which is certainly a new cool technique which we did not invent, but we certainly extended it. So if you're interested in the theory, there's a very extensive theory in our paper that was just published. And effectively what you can do then is, in this embedding space, attract similar samples to each other and repel things that are different, right? So it could be different behaviors, it could be differences in time, etc. And then you get this low-dimensional embedding. The image to me doesn't, it's not a visualization tool per se, it's really about quantifying these latent spaces. And so what we did is we started with open data. So this is synthetic data that was produced by another group that they kindly made available, where many people had benchmarked this. And so in brief, this is 100 spiky neurons, artificial, of course, neurons, where we know the ground truth latents, right? And this isn't something we have access to normally in our real data. That's what we're trying to discover. But we want to show that this algorithm can actually do this as best as possible. So this is a visualization of the zebra embedding, but here on the right is the quantification. Zebra is on the far left, and there's two features I'd like to point you to. One is that overall it has the highest R squared, so this is the linear reconstruction between the truth and the ground truth. The zebra reconstruction and the ground truth. And then we use two different types of generative models, Poisson VAE and LFADS. And then we also benchmark TSNE and UMAP because these are really popular algorithms in many settings now. And these are in equivalent benchmark settings, right? So many of the embeddings you'll see from Zebra are actually on a hypersphere because this is a nice optimization space because you can unit normalize. But this is actually with info NC plus MSE loss for those that are curious. So this is really a 2D embedding, so very equivalent settings. And you can check it out in the paper for more detail. And this is the one we put in the main figure because I think that PyVA and everything does a really good job, and I like to highlight other people's awesome work. But if you just change something about the data generating process, for example, this variational autoencoder, you can see that this does actually a pretty poor job at reconstructing these latents, and this would be reflected also in the R-square values. And so this is kind of a reminder that if you're going to use any of these tools, you need to really think deeply about what is the underlying data generating process of your data. Is it truly Poisson? Is it truly Laplace? Is it Gaussian, et cetera? Because otherwise these embedding spaces are going to be meaningless. All right, very briefly, just to give you a quick example, we use some open source data from the hippocampus. You can then do the sampling scheme. You can just use time information. This is fully self-supervised. I can post hoc color this by something like the position on the track. Then you can do a hypothesis guided. So I'm going to use explicitly position and ask if that's in my data. But one really nice feature of Zebra is that if you use a hypothesis that is truly not in your data, you won't get false friends or false structure. You'll actually get what we call an erroneous embedding. So this will just collapse onto the hypersphere. The C in Zebra is for consistency. So now if you do this across many rats that are in a similar setting, but obviously not identical setting, you can see that Zebra does a really good job. So again, this is comparing the rat 1 versus rat 2, et cetera, et cetera. And this is in contrast to these other algorithms. You can then take these embeddings and do things with them. These are only encoding models. So you could do, for example, decoding. So you can separate out these latents and then look at what they're actually doing over time. We did some benchmarking and show that this is well done. And then just maybe for those that you might be interested, I mean, the hippocampus is maybe easy, right? It's place coding. Not to offend anyone, it's a super complicated system, but from a dimensionality reduction point, maybe this is easy, where I'd say visual information is harder. So we used open source data again from the Allen, thank you very much. where in different animals, of course, they had recorded from neuropixels or calcium imaging while these animals watched Touch of Evil. Great choice. I'll ask you why later. But nonetheless, we used this visual input. We ran it through a very nice model called Dino to extract visual features, used that for training, and then did frame-wise decoding of this data, just to show you can build really meaningful in spaces. And now here, I think, is a great example of this is not interpretable to me, right? On the right, this like floating ball, of course, is actually 128-dimensional space that I can only show you the first 3 latents that were needed to capture this. But I think what's really nice is that, here's a way that Zebra can be used. You can now use this encoding model and ask for changes in decoding performance across areas, potentially across layers, and then you can look at the changes in the consistency of the latent space. So this is really a metric now. You can do comparisons across animals, areas, different states of learning, etc. And I think I have 1 minute left. Okay, sorry, yeah. I'm wrapping up, I promise. And so I think, if you take home nothing, Zebra is, or the one thing, I think Zebra is potentially very interesting for people that want to look at changes in neural population level dynamics across areas. So this consistency metric, I think, is very attractive. And it's very well theoretically defined. So I didn't go through any math today, I'm sorry. But you can look at this, and you have to trust me a little bit, but this is a well-formed problem. And so with that, another thing that we've been working on that's not in the paper, but I think is an obvious next question, is to say, can we actually back calculate who actually most contributed to each of these latents? So very briefly, if we just have, for example, a setting where you have a rat running around and maybe you're recording from entorhinal cortex, grid cells are, I think, a well-established cell type in the field, so we took that as a first pass. Again, open source data from the Mosers. And you can imagine now that you have a population of neurons, say X2 here are the grid cells, where they would actually be related to this underlying variable that's tightly linked to behavior. But there can be all these other variables that we don't understand, right? The other principal components we couldn't see, or the internal state of the animal, the hunger, things that we can't observe easily, but we still want to know about. And so the challenge is can we actually attribute which neurons to which latents, even if we can't give them names, as in Z, or if we can give them semantically meaningful names, as in C. And so very briefly, we've worked hard on this in the last year and a half to sort of show theoretical backing for that these regularized contrastive learning as a general problem setting is very good at being able to do this. So you can take your encoding model, train it, reconstruct your latents, take the Jacobian of your encoder, and then do the pseudo-inverse to build an attribution map. Very briefly, this is too busy, but it outperforms supervised baseline. So this, I think, is quite exciting. It's self-supervised, but can outperform supervised learning. And so just to wrap up very briefly the talk, hopefully I've convinced you that Zebra might be an interesting method for this large-scale data sets that you're collecting. It produces consistent embeddings, can be used with a lot of different labels. I showed you a little bit about some of the outcomes of this, and we're very excited about this, being able to do kind of more explainable AI methods on this way. So with that, I just want to give a really big shout out to all the data sets that we used. So this is from the Allen, was all the visual data. This was on Dandy, which is amazing, and this was from CRCNS. So this entire paper was only open source reuse of data, which I think is I don't know, great for the field. If you're interested, everything's on zebra.ai. Every demo notebook, you can reproduce the entire paper here. You actually see a figures tab, which you can go every single figure, every single plot you can redo in the so-called data book. And we had our first external contribution, thanks to Jerome, on the open scope data. So if you're interested in this, I would love to chat more with you guys. And with that, I just want to thank the funders that keep the lights on and you for your time and attention. And sorry for running a little over. Thanks.
Thank you very much. Any questions?
How do you do QA, so quality assurance, for your AI feature detection in the interest of not just clicking the button, right? Because usually for frequent statistics, you can inspect whether you did it right, whereas for AI, you don't know what's going in there. And the more common example is if you do like reconstruction from sparse sensing and so on, it might invent things which aren't there just because it knows it from the training data.
Right.
If you go back to one of your videos of people behaving, you can see that it detected a piano leg as a person. Do you have all of these? Yeah, exactly. So that person has two legs, but one of them is the leg of the piano.
Where's the piano leg?
In the upper right.
No. That's not the piano leg. That's the person, actually.
No, the other leg is the one that's moving. It's further to the left. It doesn't matter, but like just to illustrate the concept, like do you have people watch all of these videos and ascertain whether the interpolation is true, or how do you perform that?
No, I mean, you have ground truth data, right? So then you always compute the difference between the annotation and the ground truth. So, for example, this is a benchmark called crowd pose. These videos are all annotated, so we know ground truth of the human.
Okay.
So, I mean, yes, there can be mistakes, but I mean, this model is 96% accurate, which is one of the highest in these benchmarks.
Okay, and the videos are shared?
Yes, it's all public. Yeah, of course. Everything is public. So, I mean, this is one thing computer science has done extremely well, is that not only is it about publicly sharing data, it's about allowing developers to develop their own tools on that data in a very public way. So there's a website called Papers with Code, for example, which has all the benchmarks and, I mean, hundreds of benchmarks with the linked data, the linked papers, and the code repository to reproduce everything. I think this is the standard that we have to do in neuroscience. So, for example, with like all of these models, on the next page are banked in Hugging Face, so you can easily download the data, the weights, the models, run it in a Gradio app, run it in your own data browser, make statistics, do quality assurance checks. You have a full inbuilt evaluation set, so they're not just clicking a button. Yeah, it's a great question. But I think this is something we really need to, it's a huge amount of work though, right? Like we talked about this yesterday at the discussion afterwards with the kind of the NIH spin on it. I mean, this is a huge amount of work to just maintain the software, right? I mean, I can tell you it costs me $200,000 a year to give away Deep Lab Cut for free to everyone who's using it, because that's how much it takes to maintain and pay software engineers on this back-end stack, right? So I'm sure the Alan can also chip in, or others, but it's not cheap to have people maintain this code. So I took your question and ran with it, but someone else, yeah.
Any questions? Further questions?
Is there an assumption that these latent variables have similar time scales? For example, you can have movement that is a continuous, then you can have rewards that are discrete.
Exactly. Yes, great question. So time is a tunable parameter, but there's not a strong assumption that it has to be each latent with the same time constraint. So I don't think I have a good video of it here, but for example, even in the hippocampus, there's like a slow like gamma oscillation latent that pops up, and then other things that are very much like the position of the rat moving. So it's not baked in. It's self-supervised learning in that sense. So that's nice, and you can have more or less constraints on how, if you wanted to narrow it down as well. But yeah, great question. Yeah.
Sorry if I missed. What is the compression ratio pretty much you get with Zebra? Because you said, oh, we have 120 variables, right?
Yes.
From how many channels and
Yeah.
how well it compressed?
Yeah, great question. So here, what we did, I dropped this out of my slide talk, but maybe not. Maybe there's one that shows here. So the best performance is about 1,000 neurons. So 128 dimensions was the best, I'd say. So you can imagine, I guess this one isn't a perfect example, but around 400, this starts to statistically plateau. So it goes from 400 to 128 in this setting, in this visual system of these animals. In the hippocampus, for example, there's, in the Bujaki data set, the rat that has the most, Achilles, has 128 neurons, and you can compress it down to 3. And then we did robustness testing with topological data analysis to show like what really is the minimal kind of intrinsic dimension of this data, and it's 3. So that's obviously a higher compression ratio than in vision. So I think this could be very area dependent, and this compression ratio could also be quite interesting, I think, as another mode to interrogate systems, potentially.
All right, one more question, Joe.
I'm excited by the last part on explainable aspect.
Yeah.
So if you look at the distribution of neurons, it's going to be very sensitive because you have this nonlinear system in between. So how do you evaluate the precision? Like it's going to be very sensitive. Like you can move the neuron tiny bits because you have a nonlinear system and amplify. So I'm just curious.
Yeah.
Yeah,
of course. So, I mean, all of this, what we've done is fully in the synthetic setting. So we have control over the mixing functions. So I don't know, we've trained probably 100,000 models playing with different levels of this and sparsity of the neurons. So the long answer is it would take longer to explain than 10 seconds. But this is something we're very much interested in tackling. That being said, you can find then latents that can be to a few neurons. But this isn't... This isn't statistically robust over many, many latents, right? So here is the AUC curve, and here is the latent dimensionality. So 4, we can perfectly reconstruct every neuron back to its origin. But even by 9, we're at 95%, which, I mean, from a theory perspective, this is still very exciting. Like, the theory holds in the work that we're doing. But in a real visual system, then I think this would fall apart. So I think this would be very hard to say in a 128-dimensional space how well we could accurately reconstruct this. So I still think there's a big gap to close, both from the theory perspective and from the utility perspective of this, of mapping single neurons back to these latents. But in these, I don't know, lower dimensional latents, I mean, I'm not telling you here, some of these are hidden and some of these are observable. So this is a hybrid contrastive learning setup. So some of them are going to be easy. The more that are observable, by definition, are easier. And so this is like increasing complexity of the ratio of these latents as well. So the more complex this internal dynamics will be, like the Z's that are hidden, this could get harder. So I think there's, more work to do, but this is something we think we can handle from the theory back end.